I want to pick up where I was yesterday. The topic, of course, was the electrodynamic response of quantum materials. I gave you kind of a rather broad introduction, very pedagogical one, which is going to kind of set the stage for getting into some more details today. The point that I made, one of the points that I made at the beginning yesterday was just the tremendous range and energy scales, which is important for our studies of quantum material systems. Even if we're ultimately interested in kind of emergent low energy properties of solids, those understand these phases, very often they're contingent on not just those low energy scales, but a whole host of other energy scales. And that's our challenge when we're dealing with the electrodynamic response of solids, just this very, very large energy scales, temperature scales even, right, of the different phenomena that we may be interested in, but also the kinds of experiments, because each experiment puts us in, each frequency range or energy range puts us in with a different class of techniques. Okay, so I wanted to start with that, and then I'm going to go here. Okay, good. So what I'm going to do now is give you a bunch of techniques and examples, and we're going to continue with this theme of linear response spectroscopies. We're going to talk about the science, and then I'm going to use that. It's interesting in its own right, but I'm using that also as an entree into what I'm going to talk about next, which is nonlinear response of solids and some very contemporary things that we're working on now. Okay. If there's, as always, if there's questions, please let me know. Okay, so very large range of energy scales. Very often at the low frequency end in solids, we'll be thinking about which is very often, again, bounded by maybe the temperatures that we're interested in phenomena. We are interested in, the low temperature states of matter that come out, maybe superconductors at very low temperatures. One other very important energy scale very often is just the technical considerations that come into how low we can actually cool things down, right? So when we talk to our theory colleagues, very often they can calculate things in the zero temperature limit. And so zero temperature limit is an important scale for us. We can't ever get to zero temperature, of course, but if we're generally at frequencies above the temperature, while both frequency and temperature are small, then very often this corresponds to the zero temperature limit. So as a practical matter, this means that generally the lowest frequency scales, which are very often relevant for us for probing macroscopic chunks of things, is in the microwave range. And the canonical experiment that one does in the microwave range is that of superconducting cavities. So a superconducting cavity, or in this case, it's actually any cavity. We think of it as a metal box where we might have, and this could be a cylindrical box, we might have some small sample that we introduce inside that box mounted in some particular fashion. We have some setup where we take microwaves and we put them in through one hole and we might extract them out through the other hole. And this box, just like all confined shapes, has some particular spatial modes that they resonate, and you set up in here, it's possible to set up a particular standing waves of electric and magnetic fields. And they have certain frequencies associated. So when I send in microwaves at the frequency that resonates with the box, they can go in through one hole and come out with the other hole. So what I might do in some experiment is I might measure the transmission into this little box and out of the box. So I'm looking at the microwaves that go through and come out, and I scan frequency and I look at the transmission. And I can imagine doing an experiment. I hit that resonance and I will get transmission through the cavity when I hit that resonance, and then I get no transmission when I'm not on the resonance. And then I will do something like I introduce a sample into this box, and what happens? The resonance shifts and it broadens. We're interested in, as I kept emphasizing yesterday, into the complex response of solids, the real and imaginary parts. And so if I want to measure the real and imaginary parts, as often is said, a vector quantity, I have to measure a vector quantity. I have to measure a two-component quantity. And so I measure the shift and the broadening. And the shift and the broadening allow me, with the Fresnel equations, to work back to say what is the complex conductivity of a material in this frequency range, right? So this kind of thing has the constraint that we work only at a single frequency, but we can do very accurate experiments at a single frequency. Okay. So this is kind of a classic technique. These resonators can be made of copper. At some level, it's really like imagine some situation where you play a note on a piano and you have something particularly tuned, and then I put a brick in the piano, and now the note changes. It's kind of a rather crude measure of the properties of the brick, but nevertheless, we learned something about it in this fashion. That's exactly what's being done here. Yeah, there's a question.
When you this is the transmission of the frequencies, and but the energy needs to be conserved. So where is the energy?
So we do a transmission through, right? So when you're not on resonance, microwave, and you're trying to send microwaves through one hole, microwaves are just reflected, right? So just like always, reflected energy can be reflected, energy can be absorbed, and energy can be transmitted through. And so when you get transmitted through, then you're also absorbing most of the energy in the cavity. But if it's a narrow resonance, you're not absorbing much, right? So it's just exactly the same thing as light incident on a piece of window glass. Some is reflected, some is absorbed, some is transmitted. Does that answer your question? Good. So what can you do with that? This is a classic experiment here on niobium, which is a conventional BCS superconductor. And so that's how this experiment was done. And remarkably, so this is done by so-called cavity perturbation. A small bit of niobium was placed into a cavity. The frequency shift and the broadening is measured. And from that, you can measure the real and the imaginary parts of the conductivity. The imaginary part of the conductivity is generally proportional to superfluid density. It just kind of comes up almost like an order parameter. The real part, which is the dissipative part, has this notable peak near TC, and then it comes down and is exponentially suppressed in an S-wave superconductor. This peak near TC is what we might call, it's not generally called this in optics, but it's really the same thing. It's a Haebel-Schlichter peak. And so Haebel and Schlichter was a professor at the University of Illinois. Haebel was his graduate student. And it was one of the in the early days of superconductivity, which was one of the first real results for the kind of interesting details that gave a feeling about the microscopic BCS theory of superconductivity. It's a superconductor, but this is a peak in the dissipative part. So that's a kind of a strange state of affairs. You go into the superconducting state and the dissipation goes up, right? Which is not what you would expect. It's a superconductor. And so that's kind of a non-trivial prediction of the BCS wave function, that when you enter into the superconducting state, the dissipation first increases and then decreases. This was first seen in spin relaxation rates and nuclear magnetic resonance. It is, there's other versions of it. This is it in the microwave cavity experiment. And so this experiment, which was done really, really late in 1995, surprisingly, the very first one, is kind of a microwave cavity version of the seminal experiment, which was done by Haebel and Schlichter in the 50s. This idea of there being a resonance, some kind of increase in dissipation, it comes up in other contexts. This is a little bit older school physics now, but 15 years ago, 20 years ago, people were very interested in the notion of the 41 millieV peak in neutron scattering in a D-wave superconductor. And that's the same analogous phenomenon to this, but for the D-wave case. Okay, so this is a schematic of the time domain terahertz spectroscopy technique. So we do a lot of these kinds of experiments in my lab. And so terahertz spectroscopy, the terahertz part of the electromagnetic spectrum was traditionally always very difficult to interrogate materials. Houston said that we had a terahertz gap, that we could measure things at lower frequencies, that's say microwaves and radio frequencies, if you will, the electronics range. And at higher frequencies, that was kind of the optics or photonics range. So the terahertz gap was between electronics and photonics. It's not that we don't have enough terahertz radiation, it's that we have too much. Right now we are all awash in a bath of blackbody radiation, which is peaked in the terahertz part of the electromagnetic spectrum. So if I'm doing some experiment and I want to measure terahertz response, and I have some little chip of a superconductor and I'm sending terahertz radiation on it, and it's falling on a detector, that detector is being completely clobbered by the bath of thermal radiation it's living in. So one has to be clever. We try to be clever about how we do these experiments. The way it works, basically, is that there's an ultrafast laser here in red propagating around the table. There's a beam splitter. And so maybe I'll just wait a sec. The movie will replay. The laser goes, boom. It splits. Part of the laser goes to here and goes into a device that's called an Austin switch. It's a semiconductor switch, of which I showed two here. And then we use the laser, that's terahertz here in the middle. And then the laser kind of comes around and is used as part of the detection. So I won't go into the details of this. If you're interested in it, of course, I'm happy to talk for hours and hours about the details of how we do these experiments. But let me just say that it's time domain terahertz spectroscopy. And so this is about a picosecond long pulse. Inverse of a picosecond is the terahertz. And so this pulse has all this Fourier content that we're interested in, right? So we take the Fourier transform of that. We measure, if you will, we put a sample, let's say right there, and we measure how much radiation gets through, say the amplitude of the electric field, and we measure the phase shift. And so we measure two things, and from the two things we measure, we can get the complex response. We want to measure the complex conductivity, let's say, or some complex response function, whatever that might happen to be. We do lots of different experiments with this. You know, the kind of the most straightforward things you can do, I'll show some examples, is where you're measuring the charge response of a system. Right? So if it's a metal, or you have phonons at low frequencies, something like this. If it's a material which is, let's say, electrically uninteresting, it's an insulator at low frequencies, but it has interesting magnetic degrees of freedom, then the time-varying magnetic field of the terahertz pulse, you have time-varying electric fields and magnetic fields, can couple to, say, the magnetic dipole excitations, and it provides a very precise way of doing magnetic susceptibility experiments as a function of frequency, giving information which is very complementary to neutron scattering. We have the constraint that we only measure at zero momentum. Wavelengths of light are large as compared to the lattice scales. But we can do very detailed experiments. We have, you know, if you will, putting it in the neutron language, we have infinite beam time. And it allows us to see experiments at the true Q equals 0, which is something that in neutron scattering you can't do. And sometimes that's useful for things. Okay, so here's an example of data with time domain terahertz spectroscopy, some early data that we took on topological insulator. And so it's a good way to kind of start thinking about the kind of experiments that one does with time domain terahertz. This was bismuth selenide, okay, topological insulator. It's a thin film of bismuth selenide on top of sapphire, grown on top of sapphire, grown with molecular beam epitaxy. We measure, again, the real and imaginary parts from the transmission through the sample. We measure something that's called the complex transmission function. This is the transmission function. It tells us the amplitude and the phase of the light that's transmitted through, and it's due to the complex conductivity that's down here, right? So we measure that, and we just invert this in a simple way, and we can get that. And when we do that, that's what you get. So the red data is the real part, and the blue data is the imaginary part, and it's kind of very textbook behavior for the kind of thing you would get for a metal. This is the topological surface state that you're seeing here. It's semi-classical response. So it has this peak at low frequencies that has a width of something of about 1 terahertz. So that's the rate that the current dissipates in the topological surface state. Here, I'm just thinking about the real part for a moment. And then there's this big peak that's at about 1.9 terahertz, and that's a phonon. A lot is known about the phonons and topological insulators because materials, before we knew them as topological insulators, materials like bismuth selenide and bismuth telluride were famous thermoelectric materials where the phonon spectrum is very important. Okay? So that in the old thermoelectrics literature, that's called the alpha mode. You have an imaginary part too, and this is, as we discussed yesterday, the Kramers-Kronig transform of that. You can see it kind of very roughly, and this is not for an accident, very roughly, the blue curve looks like the derivative of the red curve, and that's due to the fact that these are even and odd functions as a function of frequency, and to kind of some approximation in some parts of the range, you can think of one as being the derivative of the other. That's kind of like, you know, just a kind of at the cartoon level to give you some kind of intuition of shapes. What we very often do here, we measure the real and the imaginary parts in this frequency range. We measure them both directly. We don't have to resort to some Kramers-Kronig transform where we would know one and have to estimate it and then Kramers-Kronig to get the other one. We could just measure them. Very often what we're going to do is we're going to measure some frequency range, real and imaginary parts, with time domain terahertz. And then we're going to use that complex information to learn about parts of the spectrum that we don't actually measure. Okay, that sounds maybe like magic, but that's of course what we do, and that's the example I gave yesterday, when you measure the superfluid density in a superconductor. You're not measuring the delta function, because that's just infinite conductivity. You're measuring somewhere else and then learning about it. Okay, so this is data that I started with yesterday. we might want to know something about this, why we have this behavior here. This is the resistivity versus temperature for early data on lanthanum, strontium, copper oxide. And as I pointed out, this is this linear in T behavior all the way up to something of order the melting temperature for lanthanum, strontium, copper oxide. This sample, is red hot by the time it's 1,000 Kelvin, and it's still the same linear law that takes you all the way from 40 Kelvin all the way up. So this is kind of remarkable, and it's something we still don't understand. When you look at data like this, the assumption is that you're looking at, the inference is that you're looking at the temperature dependence of a scattering rate. But when you measure the resistivity, there's some assumptions that go into that. When you measure the optical conductivity, you can just see it directly, right? So this is the optical conductivity measured with terahertz as a function of frequency. You have these curves which have particular widths. And I mean, this is not a level of like interpretation. It's just like from the definition of the conductivity itself. The width of this curve is the rate that current dissipates in the system. There's no Boltzmann perspective. It's not because it's a Fermi liquid, blah, blah, blah. No, this is just the definition of conductivity that comes from what we understood as the spectral response, and particularly that memory function approach. Right? So if I take this quantity here, which rolls off in this particular fashion with frequency, and I go and I kind of invert, as was asked yesterday, if I inverse Fourier transform to the time domain, I will see have a time dependence which reflects this. Okay? And then you can pull out that rate as a function of temperature. And no assumptions. The fact that it's kBT divided by Planck's constant times a number, which is of order 1. This is what's referred to as Planckian dissipation. And, it's kind of a notable result. If there are questions, people should just let me know. Okay. So now here's another example that I'll give using time domain terahertz spectroscopy. And so we've done work recently on this material here, cerium cobalt indium 5. So this is the highest TC heavy fermion superconductor that doesn't have plutonium or neptunium in it. Let's say nothing very nasty. Those can have much higher TCs, but this is a respectable about 2.5 Kelvin. This is the resistivity as a function of temperature. It kind of shows typical condo lattice-like behavior. There's kind of a decreasing temperature dependence that looks a bit like a metal, but then the resistivity starts going up, quite uncharacteristic like a normal metal. Has a peak here at about 40 Kelvin, and then starts decreasing strongly, and even at lower temperatures it goes superconducting. So this peak, where it starts increasing, this is typically inferred to be the single ion lattice, condo scale, and then there's some kind of coherence scale where this scattering that comes from conduction electrons scattering off of spins, that scattering starts to be coherent, and then you enter this regime, which is here, of linear T resistivity. And one of the things that's been inferred about cerium cobalt indium 5 is that it also has a strange metal because it's linear in T in very similar fashion. So maybe I'll just skip that, although this point also is made here, resistivity versus temperature in 0 Tesla. Maybe that's why I will talk about that. Again, you can just see the linear in T here. It was not as obvious on the previous plot, but it's a lot more obvious here. The dark black line is the linear in T resistivity. That's what conductivity curves look like. So we have the real and the imaginary parts of the conductivity, sigma 1 and sigma 2. At low frequencies, so that's the low temperature curve here, 2 Kelvin. At low frequencies, it's very non-Drude-like. You have a peak that is maybe Lorentzian, but then there's this long tail, right? Cerium cobalt indium 5 is a complicated system, which is not, we wouldn't expect to have a kind of a pure Drude-like response. We measure the real and imaginary parts, but we can still take, there is an appreciable part of the low temperature spectrum, which has a peak, which carries a lot of the spectral weight of the conductivity. And so you could infer from this, again, not at the level of, there's no interpretation here, it's just from basic definitions, that there is a large part of the current which relaxes with a rate which corresponds to that width right there. Now, linear in T resistivity, Planckian dissipation in cerium cobalt indium 5, but when you look at this in the details, what you find out is that, sorry, let me put this plot there. Yeah, okay, good. What you find out when you look at that width of that little sharp feature as the lowest temperature is that it actually goes, and that's plotted right here, it actually goes like T squared. So what comes out of this is the idea that, and it's kind of obvious all in retrospect, in a heavy fermion system, the masses are strongly renormalized as a function of temperature. In this case here, the mass is kind of doing this. I wouldn't say it goes like 1 over temperature, but it's kind of like roughly 1 over temperature. So you have a scattering rate which goes like T squared and a mass which goes like 1 over temperature. And this is the key. I think, in a sense, I don't think there's any debate to this. This is why the resistivity goes like linear in T in cerium cobalt-indium-5. It's not perhaps it's presumably not a universal mechanism for linear in T. I don't think this is what happens in the cuprates. But in cerium cobalt-indium-5, this is why the resistivity goes linear in temperature, is you have a scattering rate which goes like T squared and a mass which goes like 1 over T, and there's roughly. And so these things just cancel to give you linear in T. And again, this doesn't come at the level. There's not really any interpretation. It's just the width of this feature as a function of temperature goes like T squared. And so we've called this the idea of a so-called hidden Fermi liquid. Okay. Yeah.
Something like T-scaling.
What's that? Yeah, we didn't think about this much. I mean, maybe it's something that we should look at. At some level, the data is very well fit by a kind of a 2-component Drude model of which there's a long tail, and one can interpret this variously as kind of a frequency-dependent scattering rate, or a kind of 2-component response. And so when we make the latter choice, then there's just this temperature-dependent quantity which comes out, which has a particular width. It could be interesting to look at this. Yeah, I mean, I thought a little bit about that. At least qualitatively, our spectrum don't look like that unsimilar to the spectrum that you guys have in YRS. Good. Now, one really important quantity that we can use to understand materials, and this is something I'm quite excited by. I feel somehow when I present this to people who are not experts, they kind of feel this part of the topic is a little prosaic. But one of the things that's just really useful for us is to try to understand how is polarization of the light affected when it's transmitted or reflected through the material. So we've spent a lot of time in my group developing very, very accurate terahertz polarimetry techniques. Right? So that's the part which kind of maybe sounds where people's eyes are going to start to glass over a little bit. How interesting this could be. Ways to measure the polarization sites in the terahertz range quite accurately. And so when we started this, state of the art was 1 degree, which is not bad, right? That's a 1% precision. 1 degree is not something that you can see with your eyes very well. But over the years, this has been refined, and now we can, let's say on a good day, do something like 0.1 millidegree. So it really comes into the regime of high precision experiments. Light being transmitted through the sample could be rotated. When it's rotated in transmission, that's what we call the Faraday effect. And you can get that. The reason why we're interested in all this is that these rotations can be a probe of various kinds of symmetry breakings. So you can show, for instance, that if you break all mirror planes in the system, if you have no mirror planes, then you can get a rotation in transmission. You can also get rotation in transmission if the product of time reversal symmetry and a lattice translation is not a symmetry of a system. That's another way to get it. Okay. You can get rotation in reflection. We call that a Kerr rotation, but you only get it from this considerations about time reversal symmetry. So breaking all mirror planes doesn't give you rotation and reflection, right? So this gives you, it's kind of amusing, if you will. One thing that has obvious rotation and transmission is just plain old sugar water. So sugar water has, maybe many people have done this experiment as undergraduates. Sugar water rotates the plane of polarization of light as it passes through, but it doesn't do it in reflection. Okay. So this was something that was actually not known and people have argued about until very, very recent years. A little bit of classic optics that was still not understood until, let's say, something like the last 5 or 10 years. Okay, now one of the things that we were interested in and why we were interested in developing these high precision terahertz polarimetry techniques were to look at topological insulators. Now we've heard a lot about topological materials here. Our first topological insulator is quantum Hall system. And so a 2D electron gas and strong magnetic field, and famously the Hall conductance or the Hall resistance is quantized to very high precisions in fundamental constants. Now, very, very roughly speaking, we can think of topological insulators, 3D topological insulators, as materials where the role of strong magnetic field is played by spin-orbit coupling and in 3 dimensions, right? So this is a question that people had asked since the early days of the quantum Hall. Could you have systems that were not in 2D, but in 3D, which were like quantum Hall? And could you have systems that you didn't need strong magnetic field, but could exhibit these effects anyway? And of course, now after the topological insulators were formalized, we understand that the question is yes. You can ask the question, if topological insulators are something like quantum Hall systems, but in 3 dimensions, is there something that you can measure which is similarly quantized? And the answer we know now is yes. We can think of topological insulators as magnetoelectric systems with a quantized coefficient of the magnetoelectric coefficient. So what's a magnetoelectric? A magnetoelectric is a material that if I apply a magnetic field, I can get out a polarization. Or if I apply an electric field, I can get a magnetization. And so the crystal has to break, generally, the kind of the classic case has to break both time reversal and inversion symmetry for macroscopic magnetoelectric effects. The most famous magnetoelectric is CR203, which it was actually the very first one that was first pointed out. There's the symmetries of this material for maybe experimentalists or people. CR203 has the same crystal structure as sapphire, but instead of aluminums, they're chromiums. So it's a commensurate antiferromagnet. And it was the first material that Jalashinsky pointed out could be a magnetoelectric system. We know it as a green pigment. So it's a very color-fast green pigment. So if you see like reasonably bright, but somewhat olive green on paints, which are allowed to be outside in the sun, which hold up outside in the sun for long periods of time, that's almost certainly chromium sesquioxide, which is the very first magnetoelectric ever discovered. So, I mean, you see it everywhere when you start looking for it. There's this kind of olive green that looks a little bit like that as a powder. That's what it looks like as a mineral. And that's what it looks like in Musée d'Orsay. That's a famous painting by Monet, which this is called The Arrival of the Normandy Train. And at the station d'Orsay in Paris, that is this green here is made with chromium sesquioxide, which the classic name for the mineral is, I actually forget now, but I haven't put down on my slide, is called viridian. Excuse me. Viridian is the name of the pigment that was famous to get the green color during the Impressionist era. And it's a magnetoelectric. Anyway, what's the relevance to topological insulators? In the context of topological insulators, we can think of them as magnetoelectrics. And so whereas in chromium sesquioxide, this magnetoelectric coefficient, the proportionality between, let's say, electric field and magnetization is just some number. It's like, the conductivity of copper. It's a number that we might be able to measure, or be able to predict if we had a good enough theory, which we never do. In the context of topological insulators, that proportionality is E squared over H times 1/2. And let me, in the interest of time, not go into this, but let me just say that, what kind of experiment you can do. And the experiment that we do is measurements of the terahertz polarization. So if I have a slab of a topological insulator in the right circumstances, and I send polarized light through the sample, the rotation of that light passing through will be the fine structure constant. And so 1 over 137.041569, some number of digits. When we were setting up to do these experiments, we wanted to measure this, the fine structure constant. And I don't want to measure it. I said, we had 1% precision, 1 degree. And I don't want to say to people, yeah, we did this fantastic experiment. We measured the fine structure constant, and it's about 1 over 100. This is not very impressive. I want to be able to rattle off a bunch of decimal points. And so we developed these ways of doing these high precision experiments, and we're able to measure the fine structure constant in a topological insulator to 5 decimal points. It's not as good, of course, as the atomic physicists do, but still not bad. Okay? And that's done in these particular experiments here, which let me not tell you about the details of that. Now, one thing that we're spending a lot of time on now is kind of related in a sense, but also not, where we're applying very large magnetic fields to material systems. And again, looking at the Drude response, but seeing how the Drude response changes when you apply magnetic field. Right, so I mentioned this yesterday. So if I have the conductivity of a system, and I imagine that its response is given by this kind of Drude-esque response. If I do a DC experiment, I only measure the zero frequency value of this quantity. So when I'm doing my AC experiments, I learn, this whole shape here, its width, this area. I get a lot more information when I measure the whole spectrum. I'm not just picking off the DC value. When we're putting materials in magnetic field, we like to plot the data as a function of the response to right and left circularly polarized light. And we do that by plotting it as positive and negative frequencies, right? And so that makes sense. If I say right is e to the I omega t, left is e to minus I omega t. And one of the reasons we like that is it's the form in the right and left coordinate frame is just super simple. It's just the normal Drude expression where the pole, which at zero field is sitting at zero frequency, is just shifted by the cyclotron frequency. So you can just, by eyeball on the data, pick out how this peak shifts in this fashion. Okay, and so we've done that. This is data. We're doing this in a lot of different contexts, but this is data which came through a collaboration with Scott Coker and his group in Los Alamos, where they built a system to do terahertz spectroscopy out to really high magnetic fields. So even in some cases, we go higher than 30 Tesla. This is lanthanum, strontium, copper oxide, near optimal doping. The blue curves here are the zero field data, and then we apply a field to it, and you can see how this maximum shifts. We don't measure near zero here very well, but we can see from looking at the real part, positive and negative, and the imaginary part, positive and negative. We can fit and pull out the cyclotron resonance to really high precision, and one gets interesting information out of that, and I won't, this is how those peaks go, and that's the cyclotron resonance frequency as a function of magnetic field. And these curves here, I apologize, the colors aren't great, but the data that goes is kind of like here and going up. That's the cyclotron, that's the mass from cyclotron resonance in the cuprates. This data here is the mass that we get out from analyzing the heat capacity data. And so they're just totally different, right? So, I said to you yesterday, I gave an example of this plot where I had heat capacity on the horizontal axis and the inertial mass on the vertical axis. And there was this rough correspondence between them. And I said, well, this is kind of evidence for the quasi-particle concept, or verification of the quasi-particle concept. In this case here, we just have these two different masses in the cuprates, and they're just different altogether. And so we don't have a good explanation for that. I have some ideas, we could talk about it, but these experiments and thinking about it is ongoing. Happy to discuss more. So maybe in the final thing that I will mention before I shift to the other topic, which is nonlinear response, what I told you about here was I kind of spent some time on time domain terahertz experiments. That's the kind of stuff we do a lot of in my group. Where the terahertz part of the electromagnetic spectrum is incredibly useful for us. 1 terahertz corresponds to 40 degrees Kelvin, and tens of Kelvin is kind of a very typical scale where things happen in solids. So if you're interested in that frequency scale, then you're going to be doing experiments in the terahertz. And that's why terahertz has been useful. That's why we work so hard at it. But as I mentioned, the frequency scales that you need to measure in solids are tremendous. All frequencies can be useful for characterizing materials depending on the questions you ask. And so sometimes what we do is do other kinds of experiments. And one of those kinds of experiments is this called Fourier transform infrared spectroscopy. And here a spectrometer looks something like this. It works much more like what you would imagine for like a conventional optical experiment. In some cases, there is literally almost what you would consider to be a light bulb. And then there's a sample, and light goes from the light bulb onto the sample. And from the sample, it falls on a detector, which detects light much like a normal optical photosensor would. It's not the only way we do it, but sometimes we do it like that. And here's an example of some experiment that was done, not by me, but this was done in Dirk Van der Merel's group some years ago. The way these experiments are very often done is you'll measure the light which falls on a sample, and the light is reflected from the sample. And then you go in with a little bit of gold and you evaporate gold on top, and you do the experiment again, and you look at this ratio. That gives you the reflectivity as a function of frequency. But we want a vector quantity. We want a sigma 1 and sigma 2. We want to measure two things. We're physicists who want our complex response function. So how do we measure just the reflectivity, which is a magnitude, but we want the complex response, and we can't get that just from this because this is a absolute value squared. So there is, just as there's Kramers-Kronig relations for the sigma 1 and sigma 2, or dielectric constant, complex response, there's a Kramers-Kronig relation between the magnitude of the reflectivity and the phase that comes in from the natural log of the reflectivity. Kramers-Kronig transformed in an appropriate fashion is the reflected phase. And so this is how this is done. It's a good technique, but it's a little, if you will, dumb, because even if I care about some superconductor, which has, milli-eV scale excitations, I have to measure out to electron volts in order to have this integral work, because it technically and formally the integral goes from infinity to minus infinity. But it still can be done, and so this is an experiment that was done some years ago on magnesium diboride in Dirk van Immerel's group. And one of the interesting things here, so what you see here, that's reflectivity as a function of temperature. Here are the units, are these awful units, which I told you about in one of the first slides here, wave numbers. It's the inverse wavelength, but in units of centimeters. So that's not the language I usually talk, but 200 wave numbers is about, 10 wave numbers is about 1 terahertz. And so you see reflectivity, almost 1 here. It's a metal, so it reflects very well. And then the reflectivity, if you will, falls off a cliff and has this characteristic shape. That's what we call the plasma edge. And so the reflectivity changes dramatically when the real part of the dielectric constant goes through 0. It changes its sign there, and the reflection properties change dramatically here. And what was interesting, so the title of the paper that this data comes from was called The Two Colors of MgB2. MgB2 is a superconductor. And if you use polarized light to look at MgB2, it is actually literally 2 colors, and you can see it right there. So that's the, depending upon the polarization direction you use, it's kind of this gold color or this purple color, and that's because the plasma edge is different in the 2 directions. You can take reflectivity data like this, you can Kramers-Kronig transform it, you can get the phase, and then with the magnitude of the phase, you could then, via the Fresnel equations, reconstruct the conductivity. Okay. Let me shift to my other presentation, and while I'm doing so, I'll just ask if there's any questions on what I just talked about. Nope. Okay, how much more time do I have? 10 minutes, okay. Okay, good. So what I want to do for the remaining time then is you've built up a lot of expertise now about response functions. I'm going to tell you about nonlinear responses, and in particular, I'm going to tell you mostly about a particular technique that we've been using a lot in my group called multidimensional spectroscopy, or in many cases, our multi-dimensions is 2 dimensions, and so very often people will call it 2-dimensional spectroscopy. So let me tell you a little bit about the nonlinear optics of quantum materials. To start with, take a look at these equations on the left here, right? So this should be quite reminiscent of what we had discussed yesterday, where we were thinking that we could understand, let's say, the polarization of a system as some kind of power series in the electric field. And the first term in that's the linear response. We like linear response. It's the simplest and it's powerful. There's this kind of beautiful set of ways of analyzing data that we have this mathematical framework of Kramers-Kronig and causality to fall back onto. That framework actually exists for these higher order responses. Causality, of course, still exists, but it occurs in a much more complicated fashion. Nonlinear optics is not a new subject, right? So of course, it's a very old subject. These kinds of things are not invented by us, but the complexity of the subject means that one has to proceed very carefully. I'm very much a believer in terms of condensed matter experiment that we should be physics forward. I mean, it sounds perhaps uncontroversial, but I think there's a real tendency, particularly in modern condensed matter experiment, to kind of do complicated experiments to kind of show your technical capacities, and not going physics forward and ask, what do we really want to learn? Of course, you can always be surprised when you do some new experiment, but very often we have complicated materials, and it's amazing how much insight you can get into complicated materials from simple experiments. So if we're going to do more complicated experiments, particularly when we're thinking about correlated systems, we should be doing it for good reasons, and I hope that we have good reasons here. A lot is known, of course, about optical nonlinearity. It's an old subject, and so there are different kinds of responses that can be measured and discussed. I mentioned this yesterday. The chi2 response is generally constrained to be non-zero only when you break inversion symmetry in a system. And you can kind of, if you look at a cartoon like this, you can kind of see that that's the case here. If I have this marble and it's rocking back and forth in a anharmonic potential, there's a DC kind of, the average position when I drive it very hard is very different than the average position when I don't drive it hard, right? So the fact that there's kind of like a DC, effective average DC onset when I drive it very hard, that's called, in nonlinear optics world, that would be called rectification, right? So there's a DC offset in the polarization, which comes as a result of that. But there are different kinds and different processes. There's chi2 processes, and one of them we might call second harmonic generation. 2 photons come in and 1 photon comes out. Energy is conserved. There is difference frequency generation. 1 positive frequency comes in and a minus. You very often will think about photons that are coming in with both the field and the complex conjugate of the field. So we get positive frequencies and negative frequencies which contribute. So I can get positive frequency and a negative frequency and then emit a third photon, which is lower frequency than both. I have chi3 versions of these things. The one that I'm going to talk about today mostly is what we call 4-wave mixing. So that's 2 positive frequencies, a negative frequency, and then the system emitting on another photon that's coming out later. When we think about nonlinear response, we need to have a slightly different way of thinking about the interaction of light with matter. So when I'm thinking about linear response, very often what I used was a language, we might use the language of absorption, right? So I think, and I say something like, oh, I had a source and I had a detector and I put the sample in the middle and the light was absorbed going from the source to the detector. That language is not very useful when we think about nonlinear responses. The way we want to think about it is that we're taking a system, we're driving it with electric field. The electric field is resulting in oscillating charges. Those oscillating charges are now sources for radiation. Those sources of radiation emit radiation out into space. Sometimes they interfere with the incoming fields, and sometimes they destructively interfere, and sometimes they constructively interfere. And we measure the resultant field that comes out. Of course, that's a perfectly fine way of thinking about it in linear response too. That is what absorption is. You drive a system on resonance. That system being driven on resonance is a new source of radiation, which constructively interferes with the incoming field, and you get, let's say, no field which is transmitted because the light was absorbed. Okay? So, but that picture is going to be mandatory when we think about nonlinear responses. Again, nonlinear response is optical nonlinearity is an old subject, and the first record of it is in an early paper, well, soon after the discovery of the ruby laser. And so this is a famous PRL, which was the first observation of optical nonlinearity. And let's read what it says here. So this is a plot. This is the light listed here in funny units, tens of nanometers, all right? So that's 800 nanometers, and that's 35 nanometers. It says here, a direct reproduction of the first plate in which there's indication of second harmonic. The wavelength scale is units of 100 angstroms, okay? The arrow at 340.72 angstroms indicates the small but dense image produced by the second harmonic, right there. You see anything? No, there's nothing there. And that's because famously, there was the copy editor found the small dot, thought it was an error, and with some error in the reproduction, and removed it from the eventual images in PRL. So it's kind of amusing, right? Because this is a seminal result in optics, right? So optical nonlinearity is now literally like $100 billion a year industry, and it all started with this paper and started with the missing data. So anyway, right. So good. All right. So yeah. So it says the small but dense image is there, and it's missing. There was an erratum, and you can actually find the correct image here, but it's not as much fun as the original one. Now, let me just, again, I'm going to run out of time, so I'll just say a few things quickly. We've heard already in this meeting about optical nonlinearity. So Joel Moore was telling us, I think this picture had come in. One of the things one finds when you start thinking about these different orders of nonlinearities is that the second order nonlinearity turns out to be a very sensitive measure of the aspects like Berry curvature and Berry connection. Right? So that's what Joel had mentioned, had emphasized in his talk, was particular ways of measuring nonlinearities. This is kind of an optical nonlinearity in the form of second harmonic generation for some particular material, and which was a topological tantalum arsenide, and then their theoretical calculation, which matches that. So it becomes a very sensitive measure of these kinds of things. The second harmonic response is only possible in materials that break inversion symmetry. And so this is some data that I was involved with some years ago. The interesting thing in this is that there has been a debate for a long time about the nature of the pseudogap state in the cuprates. So there is, at low dopings in the cuprates, there is something which looks like the appearance of some gapping of the Fermi surface. It shows up in various different spectroscopic responses, but we still, after all these years, don't really know what this thing is, the pseudogap. One kind of crisp distinction you could make is the pseudogap associated with a true broken symmetry state, or is it a kind of crossover phenomena to from one kind of behavior to another? And so I think this data here, which was something that I was involved, the work was done by Dave Shea and his former postdoc, Luyan Zhao, who's now a professor in Michigan, was that it shows that there is an inversion symmetry broken phase in the pseudogap region in YBCO. So there was a distinct temperature scale where the second harmonic signal onset, and this is something which hadn't been seen previously. So it can be hard to look for these signals, these kind of structural things, in other probes. So for instance, in a transition metal oxide, obviously has a lot of oxygen. Our typical canonical probe of structure is X-rays, and X-rays are very insensitive to oxygen. But a probe like this is. And so I don't think we still understand this, but they saw something very similar in iridate compounds. They also saw a phase, which in Shea's group, which showed that there was an onset of a second harmonic generation breaking signal, which meant that there was some kind of structural transition. And they went, which nobody had found before. And then they went and with very, very sensitive X-ray diffractometers, went back and found and confirmed that it was there. So it was not the kind of thing that you could see casually, but you can see it in the SHG quite clearly. Okay, good. Didn't I start at, I started at about 10 after, I think. Yeah, is that about right? Yeah, 10 or 11 after. I looked as Eras was finishing, and it was 08. Yeah, I think it was about that. Yeah. Let me, I'll take maybe 5 more minutes, and I'll just go through this quickly, and then I'll leave some time for questions. So the thing that I want to emphasize here is these experiments that we're doing a lot of in my group of multidimensional spectroscopy. So this is a Chi-3 technique. So it's not Chi-2, it's Chi-3, which means we need 3 powers of driving field. Okay? It is, since Chi-2 is only allowed when you have inversion symmetry breaking, it's kind of the first generic optical nonlinearity, and it turns out to be a very useful one. Again, I want to emphasize that I think the only reason to do complicated experiments like this is if you think there's unique information you can get. Because it's complicated, there's no sense in doing complicated experiments on complicated materials for no good reason, right? So we can the reason is we can get unique information. So let me give you an example of the kinds of things you could see, and then I'm just going to give you 1 or 2 actual real examples. I'll give you a cartoon first, and then 1 or 2 real examples, and then I'll be done. Let's imagine we're going to do an experiment with 2 pulses. We'll call them A and B, okay? And I can drive with A and I can drive with B, or I can drive with A and B together. And I'm going to imagine a situation where I have 2 weakly nonlinear oscillators, okay? You can think of them as charged pendula that I can drive. And I'm going to, again, I can do the experiment with A and B together, or just A and just B, and I'm going to look at the response, what's the electric field that ends up in my detector, when from this difference quantity. I'm going to imagine doing them with A, B together, and then minus A, minus B. If the system was purely harmonic, I would just get 0 that comes out, right? So if it was just normal old harmonic oscillators, that's the feature of a harmonic oscillator. But if there's some nonlinearities, you'll get something non-zero, and then I'm going to plot the spectral response out of the page here, right? So these green and the blue spots, these green and red spots. Now imagine a situation where I have these 2 oscillators. Since these are nonlinear oscillators, if I go in and I shake the green one on the green frequency, and I can come in later and I can find that I've already probed it at that frequency. That's a consequence of a nonlinear oscillator. Its frequency shifts a tiny little bit when I drive it already. If I haven't driven it, and then I come in later and drive it, I can tell that I've either driven it at the right frequency previously or not. If I drive at the wrong frequency and then I come in with this frequency here, that would put me up here somewhere and I don't have any response. Really roughly speaking, the projection from the probe frequency axis to here, that is the linear optical response. I mean, just kind of, again, very much at the cartoon level. Now imagine a situation where I have those two oscillators. That was when they were uncoupled. And I can now come in and I can couple them. So what happens? If I'm thinking just about linear response with these two oscillators, what happens? Well, maybe they shift a little bit, they broaden, maybe they become asymmetric. If I have a good enough theory, I could create some story about that coupling, but I seldom have good enough theory. But in the nonlinear response, it's not that. I get new peaks on the off diagonals where I just didn't have them before. It's almost as simple as I can go in and I can shake the green guy and I can make the red guy move, right? So it's a very different situation. The other thing I can imagine is if I have some ensemble of oscillators, maybe each of them has very long lifetimes, but they're kind of in this, blob of spectral response. And the linear response is just this big blob, but each of this blob is made up of very many sharp individual oscillators, which I could imagine kind of being streaked along the diagonal like this. And I could go and I could do this experiment, and I could look at the anti-diagonal width, and I could pull out the inverse lifetime. So this is the kind of thing that we're doing. I didn't invent this technique. We didn't invent this technique. It was first developed in the context of nuclear magnetic resonance. So there's such a thing as multidimensional NMR. 2 Nobel Prizes have been given for pulsed NMR experiments doing multidimensional spectroscopy. One of the Nobel Prizes was figuring out the structure of the blood protein myoglobin. And the basic idea with this, and this is kind of an example of what NMR spectrum look like for 2D NMR, is that if I have, in NMR, you're exciting nuclei with radio frequencies. And so if 2 nuclei are close together, then you get a cross peak because this dipolar field can influence that one. But if 2 nuclei are really far apart, the dipolar field falls off in space, then the peaks are really small or absent. And so, if you know something about the structure in advance, you can figure this out and figure out what the structure is. This is the NMR spectrum of codeine. That's what the experiment looks like. We have a more complicated version of what I'd shown you previously. That's what data looks like, right? We do an experiment with pulse A, we do an experiment with pulse B, we do an experiment with A and B together. We look at the difference, and if we have some difference, that residual is the nonlinear signal. Okay, I think I'm just going to skip through all of this here because this is kind of running out of time for it, and I want to get to, what I would tell you, if I had time to tell you, is that there is a kind of a complicated structure. There are different processes. But one of the reasons that we are plotting things in the 2-dimensional plane is this is experiments done on a classic antiferromagnet yttrium ferrite. And that's what data looks like in the time domain. When we take the Fourier transforms, we have these different peaks that appear in different places in the 2D plot. And one of the features of nonlinear response, if I have a ground state, let me say, if I have linear response, if I have a ground state and excited state, there's really just one way to excite from the ground state to excited state. But if I have a nonlinear response, there are many potential paths that I could excite. And each of those paths, the chemists would call this Louisville pathways. Each of those paths encodes different information about the material system in a way that I couldn't get differently. So this response here, and they show up in different places here in the 2D plot. And so this response here, where we always have to have 3 fields involved. And so they appear here, the different fields appear as colored arrows, of which I won't explain the details. But that's like one field of A and 2 fields of B bring me to a position right there. And we call that the rephasing response. If you're familiar with the idea of spin echo or photon echo, that's the equivalent to the spin echo response. You don't usually use this perturbative language when you think about things like a Hahn sequence in NMR, but that's it right there. And then there's other ones. That's what we call the 2 quantum signal. So you kind of excite the system twice and then de-excite it. That's like what we would call the pump probe. We were doing lots of work on metals. And on metals, this is the principal and dominant response. You kind of excite the system, de-excite the system, and then excite it again. And retain information about the material responses all in the middle here. Let me just zoom through that, and I'm going to give you some examples, and I will just cut to the chase of some proposals for various things that we have talked about wanting to do. So this is some theory paper of ours from some years ago where we looked at the simplest example or fractionalization in a spin system, spin-ons, and in a one-dimensional chain. So the transverse field Ising model. So ferro spins interacting with each other with a nearest neighbor interaction, and then a transverse field where you can tune it through a quantum critical point. The linear response famously is this kind of broad blob feature, but the nonlinear response in the 2D plane has this sharp streak. And that sharp streak, a cut through the anti-diagonal direction, is a signature of the inverse lifetime. And through experiments like this, we believe that we can measure the differences between, let's say, strong disorder and strong interactions, or measure lifetimes of the two spin-on states, if you will. I'll say one more quick thing, and again, just kind of flipping through some of the stuff. One of the things we've been working on now is looking at what we call the energy relaxation rate. And the energy relaxation rate, this is in lanthanum, strontium, copper oxide, but we've done a variety of different materials. And in lanthanum, strontium, copper oxide, we pump the system, and these other metals, we pump the system. We look at this pump probe response, which I mentioned, and then we look to see how the system decays afterwards. It's kind of analogous to what some other pump probe style experiments that have been done over the years, but with lasers. The problem with those experiments is they use very high energy excitations, 1.5 eV. It's a huge energy scale as far as the physics of the cuprates is concerned and the physics of the low temperature transport. So here we take this Fermi surface and we excite it only with very low energy photons, right? A few milli eV. And we can excite the system using polarized light and look at the rate that energy leaves the electronic system. So it's a very different than the rate that I told you about before, which was the rate in the context of transport, which was the rate that current dissipated, effectively the rate that momentum leaves the electronic system. This is the rate that energy leaves the electronic system. And so it's sensitive only to the class of scatterings that remove energy from the electronic system, which in a conventional picture is just phonons. So it's a measure of the electron-phonon coupling and a quite precise one. I think I will just stop there. I'm happy to give some more examples of this if people are interested, but I think I'll just leave it at that and take questions if there's time. Thank you.
Any questions for? Thanks for the talk. I might have missed this, but did you ever say anything about how you get around the problem of like all the noise from black body radiation swamping your signal at the terahertz range? Is it like a lock-in thing or?
No. So so I didn't say it. I alluded it was a problem and then we solved it, but I didn't say what we did. So the way a normal optical detector works is that there is typically it works through bolometric detection. So there's some element inside which heats up a little bit when radiation falls on it. So it's sensitive to E squared. What this technique does, the time domain terahertz spectroscopy, is it's sensitive to the electric field as a function of time. It's kind of almost stroboscopic detection. We have these pulses coming, which are picosecond long, which are coming at 80 megahertz, and we use a laser to lock onto them stroboscopically. So in that sense, it is a lock-in technique. But we're locking in to the extent that it becomes almost a DC experiment for us. That's also how normal lock-in detection is also working, but it's essentially, yeah, I like to think of it as a stroboscopic detection. Stroboscopy, of course, you have some rotating flywheel, and if you use a flashing light to look at it, you can make it stop, and if you change the phase a little bit, you can watch it advance a little bit, and that's what we do. We have these two laser pulses, and we delay one of the laser pulses sequentially with respect to the first one, and it's essentially a stroboscopic detection, so we can measure the electric field as a function of time. And that's an advantage because the detector is sitting there at room temperature and it's being completely bombarded by this thermal bath of photons, but they're all hitting with random phase, so they don't give any net current. On the top of that, on the background of that, you have this small extra coherent signal because you have this kind of boom, boom, boom that's always being picked out with a particular electric field at a particular time. And so that's how it works around it. You gain a little bit by cooling things down, but not so much to make up for the pain of doing it.
So
Peter, on this energy relaxation rate, when you say it's non-Planckian, you mean the coefficient is small or
Coefficient
it's
is-
not linear at all?
The coefficient is small. That's what I mean. Yeah.
I see.
Well, it's not particularly, we're going to have a work that's coming out shortly where we're going to have some more things to say about exactly what the power laws are. The thing that I would emphasize in the work that we have so far is that its magnitude is much, much smaller. So it's certainly non-Planckian. It may be linear in part of the range, but everything is linear in some range. But certainly the magnitude of it is much, much smaller than KT. And so there's a few significant things about it. One is that it is an increasing function of temperature in the range that we've measured, right? So you could imagine a world, I don't think that's the world we live in, but we could imagine a world where really soft phonons were giving linear in T resistivity with a almost Planckian coefficient, but they would result in an energy relaxation rate, which was a decreasing function of temperature. So that's an old prediction that goes back to Allen, and I'm sorry I had to rush through this here. In contrast, what we see is linear in T, momentum relaxation, and also an increasing function of temperature in the energy relaxation rate. So this, I think one of the things our study does, I think it does some other things, is just completely rules out phonons as the source of linear in T resistivity in the group.
But does data allow putting some sort of bound on the exponent if the exponent exists?
Yeah, data will. Yeah, so not in the data I showed you there.
Fair
Data
enough.
will.
Yeah,
Yeah.
thank you.
Yeah.
My question is very short. Is there any sum rule for the nonlinear response that you are talking about?
Yeah, so there are some rules, but they haven't been, I don't know of, so you could also ask, are there Kramers-Kronig relations? Because very often we inherit our sum rules from Kramers-Kronig relations. There are certainly Kramers-Kronig relations because the Kramers-Kronig relations have their origin in causality. I don't know, I'm not familiar with all of this huge nonlinear optics literature. There are certainly theoretical papers which propose this. I don't know and discuss Kramers-Kronig. I don't know of any even theoretical papers which propose that there are interesting sum rules that come out of the nonlinear response. You can see it inferred in some, so if you look, for instance, at the functional forms given for like the famous paper of Soderman and Fu on the nonlinear Hall effect. They write down explicit forms for the nonlinear conductivity, and those should have some rules that are associated with them. This hasn't been measured. In the canonical nonlinear optics literature, you had a short question, but I had a long answer. In the canonical nonlinear optics literature, as far as I can tell, there's been no use of Kramers-Kronig relations or sum rules. So very often these people are concerned with 1 eV scale excitations, and they're very often not really doing spectroscopy. They have a laser and it's at 1 frequency. And so they're not doing spectroscopic response. So I think there's a wide open area here. So I think it depends. But for instance, in the case of this response function written down in the Soderman-Fu paper on the nonlinear Hall effect, the sum rule gives you the Berry curvature dipole. So it's a direct measure of the Berry curvature dipole. So what?
Independent
Are
you talking about that summing over the space and that's what's
Yeah, so it's some average over the Fermi surface. That's right. Yeah, but Berry curvature dipole is always a integrated quantity, right? So it's not defined point by point. Berry curvature may be, but the Berry curvature dipole is a global quantity.
Okay, let's thank Professor Armitage.